Lecture 12, spherical coordinates, metrics. You see, all these previous lectures, okay, will be applied to a particular case of curvilinear coordinates called spherical coordinates, okay? Metrics. Attention now. See part 3, lecture 4, okay? There we showed, okay, the initial of the spherical coordinates, okay? I advise you to go over there and see that lecture 4, part 3. So, R is the radius, phi is the polar coordinate, and theta is the azimuthal coordinate, okay? Now, in literature, sometimes you just swap. You put theta as a polar and phi as the azimuthal coordinate. But there is no problem. You can substitute, okay, swap phi and theta and derive the same expression. Now, this is Cartesian, okay? E1, E2, E3 are orthonormal, okay? You see the definition of orthonormal is delta ij. So, the position vector, which is invariant, okay, depends on x1, x2, and x3, which are the Cartesian coordinates, and or r, phi, and theta, okay? This is invariant. This is independent of the coordinate system. Now, then I draw here AR, a phi, and this here is the same, okay? So just to set this base vector A sub theta, okay? That is, I don't know yet, attention now, I don't know yet if this basis is or not orthogonal, okay? We don't know yet, okay? Now, this, the vector position here is xi ei, x1 e1 plus x2 e2 plus x3 e3. Attention now, this is invariant, so I can represent in terms of these coordinates here, r, phi, and theta. Look, it's easy, as we did on lecture 4, part 3, okay? You just project OP in OQ, okay? I call it there a row coordinate. So then I project x1 and x2 and x3. Just a trigonometric relation, quite easy, okay? Geometry, okay? Plane geometry, okay? This is R. Now, attention now. You see, here, okay, you see the definition of AR, capital R, is partial of the position vector with respect to R. So you just take the partial derivative of this, okay, partial derivative. So phi and theta remaining constant. So that's it, quite easy, okay? Now, the same likewise, A sub phi is partial R with respect to phi. Now see, this is derivative, this is calculus 1, okay? In the regular course of engineering and physics. So you derive here with respect to phi, this is the derivative is minus, okay? So this is minus over here. Okay? Now, the same A sub theta, partial R with respect to theta. You just derivate here with respect to theta and plug over here. Now, attention now. The radial basis vector AR, the polar, this is polar base vector A phi, and azimuthal basis vector A theta. Okay? So, there's a question, okay? They are orthogonal. We don't know yet. But it's easy to see because AR dot AR just simple derivation, okay? Remember that U1 dot U1 is 1, U1 dot E2 is 0, U1 dot E3 is 0. So this leads to this relation here. You see, now I have sine square and sine square. And then in parentheses, I can plug cosine square of theta plus sine square of theta is 1. So sine square, okay, combines cosine square, this gives me 1. So likewise, a phi dot a phi, you just look here, I take the dot product of a e dot a phi dot a phi. It's quite easy also, okay? Then this, again, I use the trigonometric relation, okay? Cosine square of alpha plus sine square of alpha is equal 1. So I apply this over here, and I obtain r squared. You see? Now I call GRR, G phi phi. Now the same with that over here, okay? R squared, just take the dot product of this vector with itself. See? U1 dot U1 is 1, U1 dot E2 is 0. Then you come up to R squared sine square. Okay? Now, you see, I put in parentheses this, okay? This is 1. So the result of this dot product will be R squared sine square. I didn't prove yet if they are orthogonal, okay? For sure, they are not orthonormal because this dot product is 1. It's okay, but this dot product is not a 1. This dot product is not a 1, okay? So now this guarantee ensure that the matrix, okay, in this case, okay, they are not orthonormal, okay? They are not, okay? And I don't know either this is orthogonal. Let's prove now here. You see? So, again, AR dot a phi, see, AR dot a phi, you just multiply, okay, this dot this, and apply this relation here of delta ij. Okay, it's easy. Okay, so the final r that multiply this will be 0. Now AR dot a theta, the same. Okay, I take the product of this right hand side times this right hand side over here. So this will be, in this case, okay, this will be also 0 because this cancels this will be 0. So I know now that the spherical system, the coordinate, they are orthogonal, but not orthonormal, because you see, because this term over here. Now, you see, magnitude of ER is 1, magnitude of A phi is R. You just take the square root here, okay? And also the square root of here. The square root of R squared sine square is R sine theta. It's over here, okay? So, sorry, this is, I think this is theta over here. No, this is phi. Okay, so this one here is R sine square of phi. There is a mistake over here. So this is phi. See? This is phi. Because this term here is 1. So these are a square of phi, sine in this case. So if take the square root is R sine phi. Now, the metric, attention now, the covariant metric is just the diagonal 1, R2, and R2 sine square of phi. Now, since the matrix is diagonal, the inverse is just the inverse of this term here, the diagonal. So Gij is 1 of R2, 1 of R2 sine square of phi. Okay? Remember this relation here we already derived in previous lectures. So that's it. That's important because you see, when you work with the metric, you forget from where this metric was derived. You forget. So in this case, this is extrinsic geometry. In intrinsic geometry, you forget the position vector. Okay? There we do not include position vector, we do not include vector, we do not include dot product. Okay? That's the called exterior algebra. It's not yet. So this is still the extrinsic geometry applied to the spherical coordinates. Okay?